and welcome to my presentation on Deterministic Ethernet as enabler for integrated modular avionics in the International Habitat, which is a module of the Gateway and one of Europe's most prestigious human robotic exploration projects right now. My presentation will cover three aspects. First, the main benefits of distributed integrated modular avionics, then its specific implementation for the international habitat, and a short outlook on the current status. First of all, what are the benefits of distributed IMA? The concept is to distribute all your subsystems and functions to modular data handling units, which can be freely distributed within the aircraft or spacecraft as needed, which brings several benefits. First of all, efficiency, typically also an overall reduction in size, weight, and power. Reusability, simpler integration, reconfiguration, testing, and verification, and then significant life cycle savings. Well, if it was that nice, why don't we see DIMA more often in more projects? Well, it comes with its own specific challenges. First of all, software needs to be abstracted from hardware and operating systems. And then the different software functions need to be moderated, separated from each other to prevent fault propagation, for example, as specified, for example, in the RX 653 standard. This all requires careful planning and extensive certification of shared resources, like memories or the communication network. Latencies and timing guarantees become crucial, as you need to look at, for example, worst-case execution times. Therefore, ideally, subsystems and functions are tightly synchronized, and the need for voting in software is eliminated. There are additional benefits though. First of all, increased safety and reliability, as functions can be run redundantly on 2, 3, or even more processing cores. The whole concept can easily be transferred to modern multi-core processors. And finally, one can utilize standardized processing units, which can be manufactured in larger quantities, thus also avoiding dependency on so-called black boxes from dominant suppliers. A key role in the distribution plays the network, ideally a deterministic network. And what is proposed here is an Ethernet backbone that really enables resource virtualization, partitioning, and modularity. A backbone that handles mixed criticality and, of course, allows through redundancy concepts high levels of availability. Finally, one has to look at overall robustness and making sure key system interfaces are well defined. Now, one essential challenge for distributed IMA and other safety critical systems is composability. Composability is a unique concept which allows to configure a complex system out of various subsystems, and instead of recertifying the complete system once a subcomponent or subsystem is exchanged, it's done in an incremental way, and this requires so-called composability. So if a subsystem is modified, then only the subsystem needs to be re-verified, and finally only an integration test needs to be done. This requires that the subsystems maintain their integrity and their properties when integrated. It requires, of course, again, precise characterization of subsystems and clear interfaces. And of course, fault containment within the subsystems. Now, let's look at the international habitat and step back in history. Time trigger technology was developed in the late 1990s for safety critical real-time systems. First deployed as time triggered protocol and then developed further as time triggered Ethernet, which was standardized by TD Tech, Honeywell and NASA for cross-industry use and selected for the NASA Orion MPCV and its European service module. Later, TD Tech developed its TTE controller ASIC with partial funding from ESA, and this is used throughout the RNA-6 data network, where already we see the basic principles of distributed IMA. The wider adoption of Ethernet in space applications was to some extent prevented by the lack of readily available radiation-hardened transceiver devices. But now, these days, it benefits from the newly released ESA standard for time-triggered Ethernet and the so-called IASIS. What is IASIS? IASIS is the International Avionics System Interoperability Standards, part of the Deep Space Interoperability Standards, which covers 8 key areas ranging from avionics to software and from power to docking. It prescribes for complex orbital infrastructure the use of deterministic Ethernet as backbone, i.e. Ethernet with added traffic classes. Now, this backbone will provide for redundancy, dual or triple, fault management, and network diagnostics, all fully abstracted by the network from the individual modules in the avionics. So, deterministic Ethernet means, and it supports modular integrated systems by having best effort traffic, standard Ethernet traffic, for example also supporting VLANs, rate constrained traffic as defined in RX 664 Part 7 for critical traffic, and then time triggered traffic, which can be used for both critical and non-critical traffic, as well as in the future time sensitive traffic according to IEEE TSN standards, which again can be used for critical and non-critical traffic. And all these traffic classes run in parallel on one and the same physical infrastructure. So you have safe real-time data communication over standard Ethernet infrastructure. Now, which approach did TD Tech take together with RUAG? We saw the opportunity to align with potential prime contractors on the requirements for a modular space avionics product platform to be used throughout the Gateway and Artemis. Why modular? Well, it's clearly a chance to lower development costs and program risks while increasing the potential for use, and of course then also significantly reducing delivery times, because the same modular product would be available for different customers in different areas, different programs, different continents. We decided to partner with Workspace Austria for the co-development and manufacturing of the electronic equipment and to focus on system integration and software development to bring the full power of distributed IMA to the users in the gateway. From 2016 onwards, we were in close contact with US primes, Airbus Defence and Space and Thales Alenia Space, and started in 2020 an ESA GSDP de-risking activity, trying to capture European requirements for the gateway. As you probably all know, ESA makes significant contributions towards the gateway. First of all, with the Esprit modules, which combine communication and the refueling module. And then the International Habitation Module, or International Habitat, which is developed by ESA together with JAXA, the Japanese Space Agency. The key challenges in the context of Gateway will be, once again, network composability, because the network of the gateway needs to integrate newly arriving modules. So when it starts with PPE and Halo and then integrates Esprit and the International Habitat, the network needs to continue to work, and there needs to be a seamless integration with no need for Delta certification or qualification. It will, of course, have to survive 15 years in lunar or Martian orbit. It is a human-rated project. Connectivity to standard Ethernet equipment, like laptops or cameras, is required. And similar to advanced data handling architecture, modularity is key, with the use of a middleware software called NASA CFS, NASA Core Flight Software. What are the building blocks that are being developed for this TT Ethernet-based avionics? Well, flight computers or remote interface units connect to end system cards via a driver and host interface, which could be either PCI, SpaceWire, or SPI. And these drivers, again, the driver software, supports partitioned real-time operating systems like VxWorks 6.9 or VxWorks 6.5.3 or PikeOS. The end systems then synchronize the attached network to the equipment, and of course they automatically duplicate or triplicate outgoing messages, and on the other hand, on the receiving side, pass on only the relevant messages. So end system cards connect through TTE driver, flight computers, and remote interface units to the switches, which form the backbone of the network on the gateway. The switched architecture facilitates that new participants can be added without impacting the system integrity. So a key aspect of distributed IMA. And the same core design has been utilized for the switch and end system cards based on a single silicon, the TTE controller ASIC. Let's have a quick look at CFS, the core flight software, which is utilized on the gateway. It is enhanced through features that TT Ethernet offers. First of all, time distribution, making sure all participants in the network are synchronized at the same time, and then allowing, once the synchronization is established, to link the application schedules to the network schedule. So through interrupts, the application software can be tied closely to the network schedule. This allows real-time traffic transmission with absolute performance guarantees for tight control loops. And finally, because we have abstraction, each end system can also use a simple UDP-IP interface. And this simplifies, of course, the software interfaces. At the core of the network is the TTE controller, which is an ASIC manufactured by STMicro with a C65 space process, so fully radiation hardened, and it allows to be used in both switches and end systems. A qualified version is already used on the RNA6 network. This is the so-called high-rel variant. And for the deep space environment and the human spaceflight, of course, a QMLV qualified space variant will be used in a CQFP package. This is the central device for the whole platform used on the gateway. It's used in the TTN system space 3-year compact PCI, a network interface card that will connect all the subsystems like flight computers to a TT Ethernet network. It provides 3 redundant Ethernet ports and can send and receive data via different host interfaces, includes firmware for health monitoring, and serves as baseboard also for the TT switch card. The TT switch space 3-year compact PCI is based on the same card and has an additional mezzanine card for additional 9 Ethernet ports. So it offers in total 6 1000 base T, TX and 6 100 base TX ports. Again, it includes management firmware and is the central device for loading firmware updates on the network. Finally, these elements can be integrated in TT Ethernet avionics hosting units. These can be either procured through TT Tech or third parties. A typical avionics unit would, for example, include a processor board, an end system, and 2 switch cards, but it can also be built without or with only a single switch card. Or as a TT switching unit, TSU, it would include the power supply and 3 TT switch space 3-year compact PCI cards. Let's have a look at the current status. First of all, the central device is the ASIC, which is currently in its QMLV qualification campaign, which is internally funded, but we receive co-funding through the habitation module and as pre-RM contracts. We partner with French company AROC. Already the QMLV qualification plan has been accepted, and we need to test additional interfaces because in Ariane 6, mainly the SPI interface was tested, but now also PCI and SpaceWire interfaces are being used. So a Delta test campaign and also a Delta radiation test campaign is performed. First tests already behind us, and an early summary of the radiation test results will be reviewed with ESA as part of our GSDP Phase 1 closeout. The formal end of the QMLV campaign is expected in Q3 2022. So we call this development Sonic because it is development of switch or network interface card. The initial development was for a breadboard and functional models which can be used in a lab environment. This was already completed in Q4 2021, and this includes first deliveries to European customers like Thales Alenia Space, the prime contractor for the initial habitation module IHAB. Now we are developing engineering and flight models, and this is supported by an ESA GSDP activity named Elements of TT Ethernet based Avionics under contract number 40133623, and this is done together with the Workspace Austria. This includes the qualification of both the hardware design and software, and the software development for criticality level A, of course, is ECSS compliant and will be completed by 2023. However, the software development is already based on existing IP, both for the ASIC firmware and our TTE driver, which was already qualified for use in aeronautics. In addition, there will be independent software V&V to be covered again by the International Habitation Module. Also, we have to state that the transceiver from Microchip has been selected, other long lead items have been ordered, and screening of some items has been started. We have completed or expecting to complete PDR in November and achieve system CDR in January of next year. Here is a short summary of the qualification in terms of mechanical and thermal environments. If you have additional questions, I'm all yours.